welcome back. It's been a long time. I think over a year since we recorded last.
We
good
did
to see you.
They said it couldn't be done. You couldn't record a podcast in 2020, but we have done it. It is the 31st of December.
Yeah, we have just over 12 hours left in the year.
Yep.
But who knows when this is going to actually be in people's ears.
True, yeah.
But we're recording it until
that's
what
the
counts.
thing that matters, yeah.
Yeah, good to catch up. We just spent like an hour chatting about the whole year, which has been quite a year for all of us.
Yeah, definitely.
But we do have a topic today, which is Benford's Law, which I know a little bit about, but I'm interested to hear, maybe you've done more research on the topic and can add insights to what it is. Do you want to start by just explaining what Benford's Law is?
Yeah, so I want to actually start by first saying, I think this is going to be, hopefully, there'll be like a couple of podcasts on Benford's Law, because there's a lot to it. But it's not necessarily we're going to record one after another type of situation, but it's been an exploratory adventure for me. So I think we can talk about what it is and some weird things with it, this podcast. And then in the future, after I've played around with some stuff, we can do an update, I think.
Okay, cool.
I'm not by any means a Benford's expert yet, but
I'm excited because I think of Benford's Law as like a one paragraph wiki page. I don't know what else there is to it besides what it is. But so now I'm interested. What are we talking about?
Okay, all right.
Maybe I don't know what Benford's Law is, and I'm just totally wrong.
Maybe I think it might just be me that it just blows my mind. But so I guess every article that you find on Benford's Law always starts by telling you that Newcomb, I don't know, Newcomb, Newcomb first found it in like 1881 or something like that, this law. And then he published a paper on it. It was forgotten about. And Benford, as a physicist in 1950s sometime, rediscovered this thing and published a paper on it. And now it's named after that Benford. That's a history of it. So what is the law itself? The law is pretty much, if you look at almost any data set, not every data set, but just a huge number of data sets of just numbers. And what Benford was actually doing when he discovered this is he was looking up log tables, because, in the 50s, you didn't have calculators to do logs of things. So people would calculate logs of things and just write it down in a table. And when you need to actually know what the log of some weird number is, you go to that page in a book, look it up and go, okay, that's what the log of it is. So that was his data set that he started with. And basically he noticed on his book that the first few pages were a lot more worn than the last set of pages. So basically, and in the first few, and these are organized by, I guess it must be their output value or something. So I guess it could be by the input.
It would have to be the input. Yeah.
But basically the earlier pages, those are all the lower value outputs. So they're like things that are like 1.2, 1.3 sorts of things. And the later pages are like 9.5 sort of things. So the ones that are beginning with 1 are more worn, and the ones that are beginning with 9 are less worn. And there's like, I don't know how detailed he got into this, but there's like a gradient down the way.
When you like flip pages and you read the first few chapters, but you don't touch the later chapters in a book, and you look at it like page on from the side, the pages are all wrinkled and discolored differently than the fresh back of the book that you haven't gotten to yet. So yeah, I could see a log table in a library showing that if more people are looking up lower numbers, logs of lower numbers than higher numbers.
Yeah. And so he was trying to figure out, why is this the case? And it just turns out that for a huge number of data sets, if you look at the first digit of a number that you just pick from there, it is more likely to be a lower digit number than a higher digit number. Like it's more likely, it's 30. In fact, there's a 30% chance roughly that it's a 1 and only a 4% chance that it's a 9, which to me is just, that information alone is just mind boggling. That like,
it's one thing to say like, it's more likely to be a low number than a high number, which we'll probably just talk about conceptually. But to say it is this much percent chance that it is a number that starts with 1 rather than a number that starts with 9, which is whatever you said, 4% or something like that. The fact that you can put an actual percentage on the numbers, the digits.
Yeah, both of them are pretty. The fact that it's not a uniform distribution gets me. But yeah, the fact that you can actually quantitatively say what the percentage is also just, it's another layer on top of it that just adds another level of intrigue.
And we should focus on the fact that it's the first digit. So scientific notation, it's always going to be like 1 point blah, blah, blah times 10 to the power of who cares what.
Yeah.
The 10 to the power of whatever doesn't matter. So 1 and 100 and 1,000 and 1,463,000. Those are all numbers that start with a 1. Even though 1 is much, much larger than the others, we're saying that those numbers are more likely to occur in a data set than 9 or 90 or 900 or 9 billion, blah, blah, blah.
Yeah, and it happens everywhere. So I think he noticed this probably first in the logbook, but then he looked at a bunch of different data sets, and people have looked at tons of data sets since, and there's even a website dedicated to finding data sets that are Benford. And basically things like the population of countries is an example, follows Benford's law. So if you like took all the populations of all the countries in the world and you looked at the first digit of like the population and you made a histogram of that 1 through 9, you'd find it follows Benford's law. There's roughly 30% ones and it decreases gradually down to 4% nines. It's true for like lengths of rivers. I forget what else, just bank accounts. If you like look at people's bank accounts.
Oh yeah. When I learned about this, it brought a new term to my eyes, which was forensic accounting, which I think is a really awesome term.
Yeah. So that's
that they try and capture people who are lying about taxes or income or something because their books don't follow Benford's law.
Yeah. So that's one of the things I want to get to. That's interesting.
Sorry, I jumped ahead.
But, so the other thing that blows my mind though is it's not just, okay, let's look at the lengths of all the rivers or the populations. It's also things like if I just open the New York Times and I go through it and I pull out every number that's on the New York Times and I look at the distribution of the first digit of all those numbers, it'll follow Benford's law. You're like, why?
Like not unrelated numbers, like just this things that are counted.
Yeah. Like, why would that have why would it not be a uniform distribution?
Like, why isn't 8 as likely to be the leading digit of whatever New York Times is talking about than 2?
Yeah, exactly. Yeah, that's the whole thing. And it's really blown a lot of people's minds, I think. And it's just like, it's not well understood. Mathematically, it is. There are a lot of people have written papers on this, but like the most common ones in the last 30 years or so have been from Hill and Berger. And they have a deep mathematical proof that explains like what will be a Benford system, but there's no easy understanding of why this is the case and when something would be Benford or not Benford. So that's one of the intriguing parts, is it almost feels like it's like a underlying mystery of the universe.
Yeah. If some other, I got a lot of questions now. This has opened up. What if we weren't base 10? Are things changed? Like,
yeah. So there's a lot of cool things here. What I was going to say, one of the other things I wanted to highlight really quickly too is if you go on like the Wikipedia page, you'll find that there's a Benford's law plot of just looking at not random, but physical constants. So they just take all the physical constants that they can find. And I haven't verified this one. I want to recreate this, but the first digit of all those follow Benford's law as well. So it's pretty weird. And so the other thing that that got me interested. That's what got me intrigued in it, is it just seems just counterintuitive. Like the one that really got me was either the physical constants or the New York Times one. Like, why would it ever be more likely? But okay, it is. And so I watched a lot of videos and stuff explaining this, or trying to explain it, I should say. And there's really not, I feel like no one has done a really good explanation of it. And then I've later learned that there really isn't one yet. Oh, I guess one other thing that follows Benford's law that I should mention are sequences.
Oh, so yeah, just like numerical Fibonacci, whatever.
Exactly. That's the big one that people talk about. But yeah, if you look at all the digits in the Fibonacci sequence, you take the first digit of each one of those numbers, it'll follow Benford's law. And there is an exact equation for Benford's law, by the way.
It's a function. Well, it has to be discrete, right? So it's like input, the digit 1 has a value of 30 something percent.
Yeah.
30%. The number 2 has a different value, but it's not of 1.5, is there? Or like, can you like get into the like non-integers of like how likely is 1.5 compared to 1.6?
Yes.
I didn't know that. That's interesting.
So I guess one thing to state is there is an equation that tells you what the probability of getting a particular leading digit is. And it's log base 10 of 1 plus 1 over the leading digit. So like for 1 as example, it's log base 10 of 1 plus 1 over 1. So log 10 of 2.
Okay.
And then if for 2, it's 1 plus 1/2. So it's log of 3/2. And then 4/3 and so on and so forth. And that'll tell you what the probability of finding that digit is. Now, there's just so many. I'm like trying to figure out, okay, what are all the things I want to talk about? One thing, I guess, that I also want to highlight briefly is not everything follows Benford's law. I guess that's the whole kind of interesting thing, is what does and what doesn't. But there are some really good cases where things don't follow Benford's law. One of the things that also got me into this was this recent election. There was some conservative pundits, or I don't know, people out there saying, if you look at the vote counts, they don't follow Benford's law in, I think it was Michigan or something. And therefore there's fraud here. Man, okay, I don't know where, so maybe I should back.
I remember watching a video that came out around that time by Matt Parker.
Yeah.
He's one of the number file guys, but he has his own channel.
Yeah, Stand Up
I forgot
Math.
what his channel. Stand Up Maths. Yes, thank you. He did a video on that, right? Like, why doesn't it follow Benford's law? And he explained it.
Yeah. So I guess one thing is, okay, so because it follows a lot of large data sets, people use this, like you were saying, for forensic accounting. So basically, bank accounts follow Benford's law, pretty much.
If you like looked up your transactions that you make in your bank account, you look up the numbers, the first digit of those transactions, 1 is most likely to happen. More likely to have a 1 or a 10 or $100 charge than a $30 or a $90 charge.
Yeah. And so what the IRS does is, if they want to investigate someone for fraud, one of the barometer tests that they use, that's not the right word, the litmus test, there we go, that they use is Benford's law. So they look at all those transactions and they plot it and say, is this close to Benford's law? Yeah, I'm sure they have a statistical interpretation for what close means. Sometimes they'll see some guy really just liked $40 charges, when he was cooking his books. So he just put a lot of 40s in there. So therefore, as the plot decreases, it goes from 30 to 17% for 2 to 12% to 3. Then it there's a giant spike, 50% 4, and then goes back. Yeah. So that doesn't follow Benford's law. And so that doesn't mean that there's fraud. Seeing that doesn't go, oh, there is fraud here. But it's an indicator that there's something to look at to find out if there's fraud.
Right.
So it's not a test. I think that's a key thing, is it's not a test that tells you whether there is fraud or not in forensics, but it's an indicator to look more closely. And yeah, so the people were applying this to the election, and Matt Parker explains very well, you should all watch the video, that the problem is the data set that they're collecting things from, you wouldn't expect it to be Benford, because they are looking at the number of votes in all the precincts, and precincts are designed to be roughly the same size. So they're all 1,000 people, let's say. And we expect roughly in most of the precincts around the nation, about 50% Biden, 50% Trump. So that would roughly mean we'd expect maybe a lot of 500s of people voting for one person. Right. A lot of 500s, maybe some 400s and a little 600s, not too many 300s and 700s and things outside of that. So his point is, because all the precincts are the same size, you don't have this limitless distribution of sizes, you're not going to follow Benford's law. You're going to get a lot of 4, 5s, and 6s.
When you restrict the limit of data set possibilities, it changes from Benford's law to something else, or just not Benford at all. Like heights, obviously, we don't have a lot of people that are 10 feet tall or 1 feet tall.
Yeah.
That's not going to be a popular number.
Exactly.
So most people's heights are going to start with 5.
Yeah, exactly. And it tends to be things that are limited in some capacity or set by some boundary. But those things also height is a good natural one, but a lot of them tend to be artificial as well, like precincts.
This is probably not a perfect analogy, but when you talk about statistics and you're trying to decide if it's proper to use, I don't know, like a Gaussian distribution, or if the data set approached infinite samples, then yes, naturally it would be a Gaussian, but we're just approximating. So you'd expect when it gets large, then that's when that's more valid. So Benford maybe is something like that, where it's not like if we had more people, then we would possibly get the Benford's law, but it's like when you have more possible values.
So
I don't know, it's backwards. It's like flipped because it's not that the number of samples is important. It's like the number of possible values that the samples could be. That's weird.
Yeah, there's a couple of easy ways to think about this. And I'll just say, to get to the punches, everyone, a lot of papers and a lot of people say this exact thing, that if your data set covers a large, or I guess the technical term is like if it covers many orders of magnitude, then you'll follow Benford's law. It turns out that's not actually true. It can be, but it doesn't have to be the case, as Hill points out in one of his papers. So I guess yes and no. Take it with a grain of salt. But
okay. I almost said that earlier, so I'm glad I didn't, because it's apparently wrong. But I was going to say it works when there are large order of magnitude across your data set.
Yeah. And the thing is, though, that it does a lot of times, but it doesn't every time, I guess, is the thing that Hill points out. Like, I think if you take the uniform distribution from 0 to 1, this is the example that he gives, that is not Benford, because it's a uniform distribution. You're more equally likely to get a 1 as a 9. But if you do 10 to the power of the uniform distribution, then that does follow Benford's law.
Power.
Yeah, I think that means this is part of my exploration into this, trying to learn some of these statistical probability theory terms. But I think what that means is just take any number in a uniform distribution between 0 and 1, pick one out, 0.25678, and raise 10 to that power, and then do it again for a different number, and do it again for a different number, and you get a new distribution. And that distribution will follow Benford's law. Or that new collection of numbers will follow Benford's law. But it doesn't cover a large order of magnitude. It pretty much just covers. I guess it does. I don't know.
Doesn't? Yeah.
Yeah.
Because you can 10 to the 0.00001
is really small, yeah.
Versus 10 to the 0.9. That's a pretty big order of magnitude. I don't know.
Okay. That was one of his examples. And so Hill, in I think it was 95, you can find this, a paper on Project Euclid is what it's called, not Project Euler. I keep mixing it up. Project Euclid.
Okay.
Him and Berger have this paper that talked about, here's proving when things follow Benford's law. And if you want to see why I'm a physicist and not a mathematician, you go read their description of what it means to something in scientific notation. They have a mathematical formulation that says like something is written in scientific notation, or the significant function is it takes an input, like, a number, and it outputs a number t such that t is on the interval between 0 and 10, not including 10. And it can be written such that it's between 2 powers of 10 pretty much. And it all makes sense. Like it's once you like really think about it, it's exactly what you do, but it's so much more complicated than just saying, oh yeah, you just write the first digit and then put everything else to the power 10.
Move the decimal, count the decimals.
Yeah. And then he goes into like measure theory, which is like, how do you measure the size of different things? And it's all just beyond me at this point. It might be beyond me forever. I don't know if I really want to go into it. Yeah. And it's like 120 pages or something long.
Jeez.
And so he really went in and proved like all of these different cases. And it's just very technical. But no one has come up with a simple to explain thing. So I'm just trusting him when he says that there are small magnitude data sets that follow Benford's law exactly. But one of the other cool things, though, in the paper, you could brush on this earlier, and I want to get back to it slightly, is there is a Benford's law for every digit, basically. So there's one for the second digit, there's one for the third digit. And interestingly enough, this one also blew my mind, but I just have to put this off because I'm still trying to figure out Benford's law. Let's say you're looking at the second digit. The probability of what that digit is depends on what the probability of the first digit is. So it's not like
that makes, well, no, wait. The probability of the second digit being 2 is dependent on, I could see how 1.2 is more likely than 8.2. So that in that case, the 8.2 is dependent on what 8 is.
Yeah, I don't know if it's like I said, I haven't quite looked. I don't know if it is that reasoning. That makes sense because we just said 0.8 is less likely than 0.2. So then you expect anything starting with 0.8 is going to be less likely.
Yeah.
In which case that makes perfect sense. Maybe that is just.
So I'm picturing the graph that I've seen of Benford's law's percentages, which is just, it's just like a decreasing curve, right? Kind of looks like 1 over x, something like that. I could just see how 1.2, if you just interpolate from the 1 to the 2 percentages, that 1.2 is somewhere between those, and then 8.2 is between the 8 and the 9. So it makes sense. But I also kind of remember Matt Parker video. I think that the second digit one is not 1 over x looking, it's something else. And I don't remember why, or maybe I'm misremembering it. But
it's similar-ish, but not exactly. Let's see. Man, I wish there was a way I could just share like all these tabs with you in one go.
Oh, it's kind of the same. It's just flat. The second digit can be 0 also, because there's no 0 in the first digit, obviously.
Yeah. Yeah, because you're talking about the first significant digit. But yeah, there is a general equation that does this for whatever digit you want and whatever set of digits that you want. So you could say, like, what are the odds of the first digit being a 1, second digit being a 7, and the third digit being a 5, and then who cares about the rest of the digits? So there are formula for all of whatever numbers you want, set of numbers you want.
We're kidding. This is a very large paper.
Yeah. And then I would not advise trying to read and understand it all quickly, but there is another paper that let me see if I can find it. It's on the archive and it was written this year by Hill and Berger again. It's only like 19 pages, but their thought here is there really isn't, and they kind of talk about this, there isn't like any simple explanations for it. And so they try to provide the simplest one possible without delving into too much theory in this paper. I've been working through this a little bit.
Theorem 55 on page 14. This is also a very dense paper.
Yeah. So that's why I was saying that maybe we can come back to this in the future.
Is this like one of those exercises of mathematics where it's like 500 pages to prove 1 + 1 = 2, when you can just kind of like axiomatically take it as fact that there is a unit?
I think that's what, like the first paper that I sent, the one on Project Euclid, I feel like that's what that is, right? Because this is great for podcast material, but if you go to page 6, I think that's that. So that formula there that's the definition for how to write a significant, or 2.2, the significant, I think. That whole area, I guess, definition 2.1 and 2.3 are like, here's what it means to write something in scientific notation. It's like all that, just to say the thing that we can just explain in words really quickly. And same there's a function for finding the first digit of a number. Like, why do you need a function for that? Just tell the function is, look at the first digit of the number. But yeah, so Benford's law is all over the place. There's a lot of interesting things with it. And the reason that I like it, or one of the reasons that I've liked it and have been into it, is there really isn't a great explanation apparently for it. Maybe we can talk about some of them. And then the other thing I liked is that it's accessible to play around with.
Have you seen it like in action? Have you come across it?
I haven't taken any random data sets yet to play with, but I have done some messing around. So I'm sharing a Python notebook with you. It has a couple of little plots that I have made to mess with. Yeah, I guess I want to talk about some of the explanations that I have heard so far for Benford's law that I've been messing around with. So one explanation is that I heard, I think this was in a Radiolab podcast, or maybe it was Matt Parker, one of the two, was loosely just stated as like growth, basically. Growth leads to Benford's law. And if you think about it, it makes a little bit of sense, because if you imagine counting from 1 to 100, as you count 1, 2, 3, 4, and you get up to 9, like if you stop any of those times, it's equally likely that it's any of those numbers. But once you hit 10, then the next 10 numbers are all starting with a 1. And then it'll be 20 and 30 and 40. So if you are stopping at a particular time, so if I just said, Derek, count, and I just pick a time when you stop, if you've gone over a 10, there's a lot of distance now to cover where it's all going to be ones. And then after that, now there's twos and then three. So that is roughly the loose explanation I've heard for growth being a reason why. And that's like why bank accounts maybe follow this sort of thing. If you looked at a bunch of different people's bank accounts. And I don't know how accurate that description is. I think one of the things that Hill shows in one of his papers is if you take anything that doesn't follow Benford's law and you multiply it by something that does follow Benford's law, you get something that follows Benford's law. So I think, or he also shows that if you just take a bunch of random things and you multiply them together, eventually it leads to Benford's law, which I think is partly of the reason why like the New York Times example would follow Benford's laws, because it's just a bunch of random sources. So it's this set of numbers could fall under a distribution, this set of numbers could fall under a distribution, and this set of numbers could all follow under a different distribution. And you multiply them all together, and then you get a new distribution that probably follows Benford's law.
So a while back, somebody asked on Reddit, how does Benford's law work? And I answered it, not researching, just off the top of my head. I have no idea if it's right. I just went right now to look up, what did I say 4 months ago when I answered this? So I'll summarize it. My answer was basically thinking about fluctuations in data in the like processing kind of like square root of n fluctuation in like your sample is this, you expect this number, but it's going to vary by square root of n of that number on either side. And like what numbers are possible now and likely. And if your number is 2000, I'm not going to do the square root of n exactly, but I'm just thinking about like the uncertainty around the number 2000 is a number around 1000 to 3000, like something like that. It's not going to be much outside of that range, right? Mm-hmm. But if you're like 9000, you could jump from 8,000 or up to 10 or more, right? So you're in the one as the leading digit numbers again, when you're looking at the uncertainty around something that starts with a 9, like it kind of wraps back around. And there's a lot of them that start with 1 on the other side of that uncertainty. So I think that's
like the counting sort of thought, or the growth sort of thing.
Right. I saw it in our lab. We had a vacuum chamber that had a pump with a gauge, and from atmosphere down to like super low vacuum, that's like, I don't remember what it was, 10 to the minus 12 something. I don't remember the units, weird pressure units. But it would go from 1 atmosphere down to 10 to the minus 12 or something like that. And you could watch it, like the gauge as it was pumping, and it would like go like 1 atmosphere and then 0.9, 0.8, 0.7, 0.6, blah, 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 blah. But it was like slowing every time, right? Because it's like the pump has to work harder to get that next little bit fractional change of the pressure. And then 0.9 all the way to 0.1, it would kind of like be really slow in the 0.1. And it was like decreasing the pressure. And then it flips over to the 9 times 10 to the minus 1 atmosphere, whatever. And then we go 9, 8, 7, 6, 5, 4, 3, 2, 1, and sit at 1 for a little bit, and then flip to the 9. And then 9, 8, 7, 6, 5, 4, 3, 1. And then 9, 8, 7, 6, 5, 4, 3, 2, 1. And like go really fast at the high digits and then slower in the ones, because the pump just had to work harder to like change the percentage of the atmosphere. It would take longer to reach that threshold.
Yeah, I think that's just another distribution. I think if that would follow, if you like sampled it randomly, it's going to follow.
It spent more time with the 1 as a leading digit than a 9, because it just passed through the ones and it just blows through them, because the like fractional change of like from 9 to 8 is less than the change of like, it's like it has to change by half, but like 9 to 8 just changed by a ninth.
Yeah, that's a really good way of talking about it, I think. Yeah. And then in terms of ranges, like orders of magnitude, there's another paper I'll link you to real quick, but you have to read through it. This is someone's attempt at explaining Benford's law in a simple way. And I think they did a really good job. Hill and Berger apparently have some beef with it, but I think it makes some sense. I think this order of magnitude thing I think the beef with it is that it's not always true, but it's true a lot, I think. But they basically talk about if you have a distribution of numbers, particularly if it's a log normal distribution, meaning it looks like a Gaussian when you have it plotted on a log x axis, or the x axis is plotted on a log, that basically you can make an approximation that if you, they call it a striped hat. Yeah.
I started, so I'm like, it caught my eye. The law of the stripy hat is the subject of that section. And I'm like, that's really interesting. I started reading it. And then in my head, I'm picturing a cat in the hat, like stripes in like a cylinder, going upward. And then I scrolled to see the graph. I'm like, oh, that's what they meant.
Yeah,
so they mean like
vertical stripes
in like a Gaussian distribution that someone's wearing on their head. Their hat is the Gaussian distribution.
But what they basically argue is you could make, the stripes would be all the digits that start with 1 in that distribution, let's say, or whatever digit you want. And you can approximate the number of those by just looking at the x-axis. Like, what area of the x-axis do all those stripes take up, those vertical stripes? And if you have a few stripes, like maybe 1 or 2, it's not a very good approximation because you got a lot of curvature going on the Gaussian up top. But if you have many stripes, then the width of each stripe gets smaller and it gets closer to approximating the curve part of the Gaussian at the top of it is roughly flat, the smaller and smaller you get. And so basically they're saying, okay, eventually what happens is if you get so many of them stripes, then it'll converge to the area that's covered on the x-axis for any distribution, or almost any distribution, I should say. And therefore, that's like saying when do you get more stripes is if it's a log normal plot is when you cover many orders of magnitude. You'll get many more cases where 1 is the start of it. Then you add to that, okay, I haven't said anything about why 1 would be more probable or not than 2 in this. It's that if you look at like if you look at a log plot or like just a log space, right? If you go from 0 to 1, that gap is huge. Then you go from 1 to 2. Okay, it's not particularly, it's smaller, but it's still kind of big. And then you go from 2 to 3, it gets smaller, and it keeps getting smaller and smaller, the gap, until you get up to 10. And then you get a big gap between 10 and 11, or 10 and 20, sorry, and so on and so forth. So it's like, everything between 1 and 2 are the things that start with 1, basically. And so it covers a larger area. Mm-hmm. So therefore, the stripe is bigger for that section of the plot than it is for like the 9s. The stripe, you have smaller stripes. And so therefore, you're going to have more area, or more likely that it would be a 1. I don't know if I'd explain that too well or not.
I was getting tripped up because I'm looking at their hat thing, their drawing, which I think is different than what you're saying. But yeah, I get it. I get the stripes. And yeah.
If you scroll down just beneath the hat, they have this equation here where it's, okay, write a number in scientific notation. Mm-hmm. Log 10 of that number is equal to, R times that number. And then you're looking at log base 10 of the scientific part, the real part of the scientific number, not the times 10 part, mm-hmm. plus some integer. And so it says the next part down is, look, if the log of your number is between 0 and 0.3, 0.3, then that number is going to begin with a 1. If it's between 1 and 1.3, that number is going to begin with 1 as well. And then between 2 and 2.3, it's going to begin with 1. So you pick an integer, and then you add 0.3 to it. Mm-hmm. The log of that number, anywhere of those numbers in that range, will begin with 1.
Got it.
So that's a wide stripe of things. But if you do it for 2, it's going to be between like 0.3 and 0.47.
I see. I guess, basically. I get it. I get why the log is important now. I get it.
Yeah, so it's a smaller and smaller stripe. Mm-hmm. And so basically the two things are, okay, logs of things give you larger stripes for 1s than it does for 9s. Mm-hmm. And the more stripes you get, the closer you are to just looking at the x-axis and you don't have to worry about the distribution. So eventually if you get enough stripes, meaning enough orders of magnitude, it'll follow Benford's law. So they say almost any distribution would follow Benford's law.
I just had a dumb thought of like, oh, we have data that follows Benford's law. Let's double it. Then I'm like, oh, I tricked it. That's not going to follow Benford's law because now we'll only have things that start with 2 and 4 and 6. But that's not true, because when you get to things that start with 5 and you double it, you're now back to the ones, and you have a whole lot more ones now. And I'm like, damn it, Benford's law got me again. I thought I could outsmart it and just multiply every number by 2. But nope.
Yeah, so actually I have a cool thing I can show you here. So one of the things I wanted to do was, as far as I can tell, there's no great explanation for this, and I've been trying to figure it out. But I found that it's really easy to play around with Benford's law yourself, because computers are pretty good at generating pseudo-random sets of numbers. And so you can just put it in a Python program and play with it however you want and see things. And so that's what I did in this this notebook. Okay, so when I first ran across this, I thought, all right, there's no way that this is true all the time. It can't be, because of like a dice, right? It would mean a dice wouldn't make sense. It'd be saying if you were to roll a dice, you'd be more likely to get a 1 than a 6.
Oh, okay.
We all know is not true, right? Mm-hmm. But, so my first order step was just to, prove that to yourself, Zach. Make sure what you think is true. And so I took some code and I essentially made a billion-sided die.
Okay.
And I said, just pick 100,000 numbers from my billions, roll the billion-sided die 100,000 times, and tell me what the leading digit is. And I plotted it, and that's that first plot there on the left. And lo and behold, the world is fine. It's exactly what you expect.
Yeah.
You get 11% across the board, 11% chance of getting a 1, 2, 3, and so on. So that was good. That made me feel good. I was in an existential panic until that moment.
What's the red in the graph? What
the red law is Benford's law.
Okay.
Yeah, exactly. And then, so I'm not sure what that second plot is right now, but skip that, scroll down. This is a fun little maybe puzzle, but I think you've already explained it. Go ahead. Yeah, so I think maybe you can just figure it out, right? So the first set is you just take that random distribution of the die that you've rolled, and you multiply it by 1. And then, so it looks just the same as if you didn't multiply by anything, obviously. And then the next plot is what if you took those numbers, you multiplied it by 2, and then 3, and so on and so forth.
Right.
And what you find when you multiply a uniform distribution by 2 is there's a way more likely chance that the number is going to start with a 1,
right?
Almost like 50% chance. In fact, it's probably exactly 50, I bet, somehow. And that if you do it with a 3, if you multiply a uniform distribution by 3, it's likely that it'll start with a 1 or a 2 at about, that looks like 35% chance. And then everything else is like really low, like 4% chance or something. And it keeps, so if you multiply by 4, then 1, 2, and 3 are likely. 5 is 1, 2, 3, 4. 1, 2, 3, and 4 are likely, and so on and so forth. So any thoughts here? This is what I like about it, is you can just run these sort of like little tests and kind of mess around with things and see what happens.
So I went through the 2 times thing, multiplying every number by 2, and the only way to have the leading digit that's not 1 is 2 how would you get a 3? Oh, if it was like a 1.5, then you would have a 3. 1.5 times 2 would be a leading digit of 3. Basically, very low chance of having a leading digit of 2, 3, 4, 5, 6, 7, 8, 9, because when the second you get to the 5s, doubling it is going to be a number that starts with a 1, a leading digit of 1.
Yeah.
Doubling any number between 5 and 9.9999 is going to be something between 10 and 20, which all start with 1.
Yeah, exactly. So it's got to be 50% then, or slightly more than 50%, because it's 50% of the space plus the 1. I guess you don't multiply. If you multiply the 1 by 2, then you're at 2. So 50% of the space.
Any of the numbers between 1 to 4.99999. 1 to 5, but not including 5. Doubling it would give you something that's not starting with 1.
Yeah.
And then after that, all the numbers start with 1.
Yeah, exactly. Yeah.
Okay.
And then you can work the same logic out for 3, 4, multiplying by 3, 4, 5, and so on and so forth. So that was just one interesting test I did. So I need to play around with this more. I did one more test so far, where this was the counting theory, where what I did is I counted at some rate. So either I would just increase my number by 1 every time, so that's what the first one is. So it says, start at 1, for instance, and count up by 1. And you're going to randomly stop at some number, which is, I think there's a, 1 in 100,000 chance that you stop each time you increase by 1. So eventually you hit that. Luckily we have computers and you stop, and then you look at the leading digit of that number.
Yeah.
And that's, if you look, that follows Benford pretty good.
Yeah.
Like, it's not perfect, but it's close. There's a bit higher chance of getting a 1.
Yeah.
After this is doing 3,000 repeats of this. So it's not the largest sample size, but then I did, okay, what if you increase by a random number? So instead of going up by 1 each time, you go up between a number between 1 and 9 randomly. And that also follows Benford's law pretty well. Then I did a quadratic increase, which follows Benford's law exquisitely.
Right.
So that's just, I think you just square the number every time. And then an exponential increase where you like multiply it by the same value, whatever it is, every time. So if you start with a 4, you multiply it by 4, multiply it by 4, multiply it by, or no, I guess in this case, I'm multiplying it by 2 every time. I multiply it by 2. And it turns out if you just look at a sequence of numbers, so you don't do this growth thing, you just look at the sequence of 2 multiplied over and over again, then you actually get a distribution that follows Benford's law exactly as the number of times you do this goes out to infinity.
That's cool that you programmed it and we can simulate it with anything we want. And I started thinking about functions and then constants and thinking about the E, Euler's number, and then pi. Those don't follow Benford's law, right? The digits of pi.
I don't know.
They're not leading digits. They're just digits.
No, but if you took it like as a sequence, you said, okay, pi is a sequence of numbers.
Yeah, but is it a sequence? It's just a set, like...
Yeah, I guess there's no formula for that sequence, right?
Right.
Unless you want like a Fields medal.
Yeah. Let me quickly write down the formula for all the digits of pi. I'll generate them.
Wait, actually, I think there is a formula for generating the nth digit of pi. Really? Yeah. I think it's in hexadecimal.
Okay.
You can convert back to decimal. But I think there is a formula for generating any n digit of pi. It's just it never repeats.
Got it. Yeah, what's the last digit of pi?
But yeah, so I haven't finished goofing around with Benford's law, but I think I have a couple more things to say about it. And then if we want to ask questions and do some stuff, I'd be down. But so yeah, basically, I think I just like that you can do these tests really quickly on your own and just mess around with things. I think that makes it, and it's fun to think about why would this follow Benford's law and why would this not follow Benford's law. And sometimes you can figure it out and sometimes you can't. But it's a bit of a mystery. And, so I have 2 other things. I'm sorry, I keep adding things. There's a lot on this. So one last quick paper, I guess it's not a quick paper. Wait, no, I did send it to you. The one on the archive, let's see. If we scroll down to, so this is Hill and Berger's attempt at simply explaining what follows Benford's law, or at least trying to do it. So if you scroll down to page 8, I think that's the first time they mention, page 5. Since they kind of mathematically figured it out, they said, what properties characterize Benford sequences and random variables?
Okay.
So then they list the three properties. They say, okay, these include 3 basic properties of a sequence of constants or a random variable that are equivalent to it being Benford. So if it's one of these 3 things, it's a Benford thing. So this is interesting. I don't know why. The fractional parts of the decimal logarithm are uniformly distributed between 0 and 1.
Okay.
So I think that basically says if you take any number and you look at just the decimal part of it, you take the log of that it has a uniform distribution between 0 and 1 of all the numbers in your data set. So it's equally likely to be any of those numbers between 0 and 1. Which I don't know why that would be the case, but okay. The distribution, its significant digit is invariant under changes of scale. So that's cool. So that's if you change your units, it will still have the same distribution. And then this answers one of your earlier questions too. The distribution of its significant digits is continuous and invariant under changes of base. So if you are not doing base 10, but doing base 16 or 2 or something, that's actually a sign that if the distribution doesn't change and it's continuous, that it'll follow Benford's law. If you go down to eventually page 8, he talks about the 3 properties of what makes sequences of constants or Benford, like it's not a polynomial increasing or decreasing sequence, and so on and so forth. And so he lays out some rules that I'm working through exploring a little bit right now. And at the very last, on page 15, he talks about common errors in Benford's law, which the first error is, to be Benford, a random variable or data set needs to cover at least several orders of magnitude. That is an error in that people. Exponential sequences can generally be assumed to be Benford. And I guess that's not always the case, because you can pick particular choices of exponentials that aren't Benford. Typically rational repeats of 10. Like 10, because if you're working in base 10, things with 10 tend to not be Benford, because you always get ones, right? If you take the log of 10 to the n, it's always 1, right? Is that what it is? No, it'd always be n. I don't know off the top of my head. But yeah, so he goes through these errors. And this is something that I'm working on, parsing together and playing around with a little bit. And I think the final little thing I want to say on Benford's law that I haven't looked into yet, and I'm going to squeeze this in as this is a physics podcast. Why are we talking about just some random math thing? Okay, I can squeeze in some physics. Because math is really interesting still. It's still an interesting thing. And there's a lot of distributions in physics that are useful to know. But apparently there are some ways to derive Benford's law from looking at entropy. And I haven't began to process that yet, but that sounds really interesting to me and something I'd also like to look at.
Error 4, there are relatively simple intuitive arguments to explain Benford's law. Got it. So don't try.
Oh, in the archive paper?
Yeah, the last error. The last thing before the end of the paper.
Yeah.
There are relatively simple and intuitive arguments to explain Benford's law in general. That is an error.
Yeah, like that. But I think the thing is, people want to do it. And I think this is stated in a weird way, I think. Maybe I'm wrong here. But I think the idea is that we don't have any yet. But I don't think that means that there isn't one out there, or one can't be discovered. But there's not like any... There's basically like you can poke holes in any of these generalities that you find online. Like one of the ones I saw that got me also interested in this was from Sal Khan and Vi Hart, actually. Mm-hmm. We're talking about Benford's law on one of their YouTube channels. And they were saying like exponentials follow Benford's law. And the way they explained it was, if you again looked at like a log axis, again, the distance between 0 and 1 is huge, and the distance between 1 and 2 is smaller, and it keeps until you get to 10, and then you repeat this. And they said, okay, now if you plot a exponential increasing function on here, on that axis, not create like an XY plot, but just like mark all the points where you would land if you like did integers, let's say, on that, you'd find, hey, they are equally spaced apart on that axis, on the log axis. And therefore, just the odds of landing in between 0 and 1 are much higher than 0 and 2, because if you just equally space something out, that'd be the case. But I mean, to me, that kind of says like everything should be, almost everything should be Benford, just by throwing random things at a dartboard. And so I think like a uniform distribution would be Benford, but it's not Benford. Yeah, I feel like their argument is like one of these ones that's like subtly seems generally true, but is not really accurate. Why the log axis? Like, why does that matter? And then B, like I think you can find examples that you would throw at this dartboard of the log axis that wouldn't follow Benford's law, but like on the dartboard, it looks like they should, basically is all I'm trying to say.
I'm still weirded out that there's like an actual percentage per digit. And so I have not read this paper. Does this paper go through and prove of each digit?
Yeah, I think it comes from, maybe it's the FEWSTER paper does it better, or I think it's also on Wikipedia. But I think the equation just comes from, okay, if a number begins with 1, let's say, if it falls between 1 and 2. And if you take the logs of all the numbers, then a number falls between 1. If it's between log 1 or log 2, then log of that number will be in between them. And then I think from there, and you can replace 1 and 2 with just whatever, a digit and a digit plus 1, or an integer and an integer plus 1. And then I think you manipulate that equation to get, it's a briefly stated thing here, but to get the equation that ends up being Benford's law, which is just saying that the width of the stripe then in log terms is log of your digit plus 1 minus log of your digit. So D is typically the term used. So log of D plus 1 minus log of D. And then you use your log rules and you get Benford's equation, log of 1 plus 1 over D is the value. That's all. That's literally all the derivation is. You just say, okay, numbers between it, if it's the thing that makes sense, if it's between 1 and 2, and then take the log of everything, and then you say, okay, how wide is that distance? What is the length of that distance? Well, it's the high end log 2 minus the low end log 1, and that width is the percentage from Benford's law. It's 30 point something 1%.
I should have gone to the Wikipedia page from the beginning. I see what you're talking about now. But it does look like they do it kind of backward. Like Benford's law is numbers that follow this rule. But like, where did that rule come from? Like they give the equation and they say Benford's law is things that follow this equation. But I wonder, it has a source, so I'm assuming that source goes through it. But
yes, I talk about it like a couple paragraphs underneath, I think, which says, for example, a number x constrained to lie between 0 and 10 starts with the digit 1 and 9. And then so it says, therefore, x starts with the digit 1, and then they take the log of everything, and you can figure out what the interval size is. So that's just, I guess the question really is, why logs of things?
Yeah, that.
And I don't think there's an answer to that. I think that's something that's not quite known yet. And then another paper, I'll send you the last one, I think. It's another one by Berger and Hill, and it was written in 2011. And it's pretty much saying that there is no explanation for this. The real question in the end is why logs of things is the thing that matters.
Mm-hmm. Berger's all over this. Well, let's tie it back to a couple things. The original source being the looking up log tables in books and seeing that the lower numbers were more worn. I've never seen a log table. Well, that's not true. I totally had log tables in the back of my math books growing up. But are they organized with 1 and the 10 and then 100 all in the same, like, quote unquote chapter? Or is it must be, right? That's weird.
Yeah.
Or do they just do powers of 10? And is there there's probably some log rule where it's like 10 to the 2, you can figure out the log of 1 times 10 to the 8.
Yeah, that's just you
don't need to know the times 10 to the part. You just need to know the 1 point.
Yeah, because if it's log 1, it's whatever that value is.
Yeah.
But log 10, I guess, maybe is where we should start. And then log 100 is just 10 squared, so it's 2 times log 10, right? Mm-hmm. And then 1,000 is 3 times log 10. So yeah, there's probably write your number in scientific notation, and then just take all you need is the number, not the times the 10 to the part value, and then you just multiply your number by whatever the n is, and your 10 to the n part, your answer, and you get the value out.
Yeah. That's like, log A times B is log A plus log B.
I think it's, I think
you're right that the log in that case is just times 10 to the whatever is just the whatever.
Yeah.
So
you just add the value to it.
Right.
Is what it is, not multiply, but
yeah.
But yeah, so I guess you only need really the log of maybe all the
first part
between 1 and 10,
Mm-hmm. To wrap this episode, and we can follow up with more details as you dig into those 100 and something page math papers.
Yeah, I'm definitely not going through. I tried sigma algebras. I've tried to figure out what the heck that was. And I just don't understand math. I don't know why, like the pure math. I don't know why they have to make. Yeah. I feel like they just say a thing, but they don't tell you why they're saying that thing. They're just like, here's the thing. and then I don't understand it because I don't know why they're saying it. And I just keep wondering, why are you saying this? And they don't care. They're just like, that's the definition.
Yeah.
So I probably won't go through that paper.
I'll jump back in when you get to the entropy discussion.
Yeah. But yeah, so I think that would be fun. I'm going to keep updating this notebook and we'll see what. So one thing I wanted to try is looking at like decay times of hadrons or something. Is it hadrons? Is that what they're called? What's the two? Yeah. There we go. Thank you. I should know this. We had a podcast.
The quarks systems in general.
Yeah, so like decay time of like mesons or something, for instance. Look at all those and see if that follows Benford's law, or just try to find things like that and just mess around with. Because I feel like if something doesn't follow Benford's law, that's just like financial forensic accounting. Yeah. It's like a hey, what's going on there? Right. Let's look at that. Right. But I don't think that will be the case. I think they'll all follow Benford's law.
Speaking of using decay times as a source of data, in our undergraduate advanced lab, the first lab you do is just basically understanding statistics, and like the source of statistics, because it was a physics class, was decay counts of like some nuclear source. I don't remember what it was, but basically it was like, wow, we're doing nuclear physics. Like, no, you're just counting, and we need something that has lots of numbers, and decays of a radioactive substance is a lot of numbers all at once. So let's use that.
Yeah, good. It's a good number generator, not quite random. But, I mean, I guess it is, but it's not a uniform distribution.
So to end this, I think it's fun, since we're talking about Benford's law, just laws of things, names who are associated with laws. You said Benford wasn't the first one who actually figured this out. There's a law of naming things after people who didn't actually find it, but were the second person to find it, which is Stigler's law. And so Stigler's law says that the thing that is actually the person that the thing's actually named after isn't the person who discovered it. It's the second person. That's who gets the name.
You know the best part about that? I don't know if this is true, but I read it in one of the articles I was reading about Benford's law, actually. Stigler was the second person to
exactly
this law.
Stigler's law is an example of Stigler's law.
Yeah.
I love it. Cool.
So try to be the second person to discover something, basically.
Then you can name it. Let's, I'm excited for entropy discussions around this. I think I'm excited to talk about thermodynamics at some point, so we can tie that in maybe. It'll be a nice bridge between topics. I got a whole... Yeah. My 100-something page paper has been this huge website talking about modern thermodynamics, so...
That's interesting. Yeah. Thermo is maybe my least favorite subject, but I'm excited to understand it finally.
Yeah, maybe. We'll see.